Assalamualaikum warahmatullahi wabarakatuh. Hello guys, Salsa's here. Welcome to my video. In this video, I'm going to explain to you a solution from my functional analysis final examinations question. So as you can see in here, I have my final test question. There are 4 questions in here, but I only talk about number 3, okay? Right here. So let's see together. Number 3. Let x is equals to c sub 0 of r be the space of continuous functions vanishing at infinity. C sub 0 of r is equals to f is an element of c of r where the limit of f of x as the absolute value of x approaches to infinity is equals to 0. I'm sorry. Okay, define the norm by norm f is equals to the subprimum of the absolute value of f of x. X is an element of R. These questions wants us to prove that x and the defined norm is a Banach space. So that is the question. Now let's jump into the solution. So I have typed the solutions right here. From the questions before, we already know that x is equals to c sub 0 of r and the definition of the norm f. Now, we will prove that x and the defined norm is a Banach space. Before we show a space is a Banach space, we have to know the definition of a Banach space itself. So, Banach space is a complete normed space. Banach space is a complete normed space. So, to show a space is a Banach space, we have to show that that is a normed space first. After that, we're going to show that this is a complete space, just like that. Okay, so we're going to show that x and the defined norm is a normed space. A space is called a norm space if it satisfies 4 conditions. The first conditions, as you can see in here, the norm of f should greater than or equals to 0. Right now, using the definition given from the question, we know that the norm of f is equals to the subprimum of the absolute value of f of x. Okay, as we know that the subprimum is the least upper bound, so automatically we have the norm of f is greater than or equals to the absolute value of f of x. Why? Because the norm of f is the subprimum of this. Okay. Now, based on the definition of the absolute value, the absolute value of f of x is greater than or equals to 0. Now, from this inequality, we have the norm of f is greater than or equals to 0. So this space satisfies the first conditions. Okay, it satisfies the first conditions. Now let's jump into the second condition. The second condition stated that the norm of f is equals to 0 if and only if f equals to 0. Since this statement using if and only if, so we have to prove from left and from right. So from left, we will show that the norm of f is equals to 0, then f is equals to 0. Let the norm of f is equals to 0, then based on the definition of the norm of f, we have the subprimum of the absolute value of f of x. X is an element of R is also equals to 0, right? For every x is an element of R, we have, I guess I have explained this in the first condition, so I'm not going to talk about it more. Okay, since the norm of f is equals to 0, then the absolute value of f of x is equals to 0, right? Because the subprimum is 0, of course, the absolute value of f of x is 0. That's why we have f of x is equals to 0. So we have proved from left. Now we're going to prove from right. So from right, we're going to show that f is equals to 0 if then if f equals to 0, then the norm of f is also equals to 0. Okay, let's see from right. Let f is equals to 0, then of course the absolute value of f of x is also equals to 0 for every x is in R. It means that the supremum of the absolute value of f of x is also 0, right? The supremum of 0, 0. So we have the norm of f is equals to 0. Since we have proved from left and right, we know that we have the norm of f is equals to 0 if and only if f is equals to 0. So this space satisfied the second condition. Now let's jump into the third condition. So the third condition stated that the norm of alpha f is equals to the absolute value of alpha times norm of f for every f is in x and alpha is in R. Based on the definition of the norm, we know that the norm of alpha f is equals to the supremum of the absolute value of alpha f of x. Based on the property of the absolute value, we can write the supremum of the absolute value of alpha times the absolute value of f of x. Now, it is equals to the absolute value of alpha times the supremum of the absolute value of f of x. Okay, so since this is equals to the norm of f, we have that alpha, the absolute value of alpha times the norm of f. So we have this is equals to this. It satisfies the third conditions, just like that. Okay, now let's see the fourth condition. The fourth condition stated that norm of f sub 1 plus f sub 2 less than or equals to the norm of f sub 1 plus the norm of f sub 2 for every f sub 1, f sub 2 is an element of x. Based on the definition of norm, we know that norm of f sub 1 plus f sub 2 equals to the supremum of the absolute value of f sub 1 of x plus f sub 2 of x. X is an element of R, and this is less than or equals to the supremum of the absolute value of f sub 1 of x plus the supremum of the absolute value of f sub 2. And as you can see in here, this is equals to the norm of f sub 1 and this is equals to the norm of f sub 2. So we have that this is equals to the norm of f sub 1 plus the norm of f sub 2. Therefore, we have norm of f sub 1 plus f sub 2 is less than or equals to the norm of f sub 1 plus the norm of f sub 2. Since this space is satisfied all four conditions, then this is a normed space. Okay, so we have proved that this is a normed space. Okay, next we will show that this is a complete space. Using the defined norm given from the question, we already know that the norm of f is equals to the supremum of the absolute value of f of x. Now, we're going to take any Cauchy sequence f sub n on C sub 0 of R. Well, based on the definition of Cauchy sequence on norm space, we have that for every epsilon positive or epsilon more than 0, there exists capital N in natural numbers such that for every m and n is greater than or equals to the capital N, we have norm of f sub m minus f sub n is less than epsilon. In here, we will show that every Cauchy sequence f sub n on C sub 0 of R converge to f in C sub 0 of R. So to show this, I will show the way in 3 steps. So the step 1, we will show that every Cauchy sequence f sub n in C sub 0 of R formed Cauchy sequence on R for a fixed x. So this is the first step. This is what we're going to do in this step. Okay, now take a fixed x on R such that the absolute value of f sub m of x minus f sub n of x is less than or equals to the subprimum of the absolute value of f sub m of x minus f sub n of x. Well, I guess it's pretty clear to see since this is the subprimum of this, okay? And as you can see, this is equals to the norm of f sub m minus f sub n based on the definition of the norm itself. Now, since the norm of f sub m minus f sub n less than epsilon, where do we have it? We have it from here, as I've explained before. Then, for every m and n is greater than or equals to capital N, we have for every epsilon positive, blah, 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 we obtain this, less than epsilon. So based from this inequality, we have the norm, the absolute value of f sub m of x minus f sub n of x is less than epsilon. Therefore, it's obvious that f sub n of x is a Cauchy sequence on R. Since R is a Banach space, then every f sub n of x on R converges to f of x in R. Or we can write as f of x is equals to the limit of f sub n of x as n approaches to infinity. Now, that is step 1. Let's move on to step 2. In step 2, we will show that f sub n approaches to f as n approaches to infinity. So before we have that the absolute value of f sub m of x minus f sub n of x is less than or equals to the norm of f sub m minus f sub n. Let m approaches to infinity, then f sub m of x approaches to f of x for every m is greater than or equals to capital N. Then, for every epsilon positive, there exists n in natural number such that for every m n is greater than or equals to n, capital N, we have the absolute value of f of x minus f sub n of x is less than epsilon for every x in R. So, the norm of f minus f sub n is equals to the subprimum of the absolute value of f of x minus f sub n of x. And it is less than or equals to epsilon, which means that the norm of f minus f of f sub n approaches to 0 as n approaches to infinity. Or as we can say, f sub n converges to f. That is step 2. Now, step 3. In step 3, we want to show that f where f sub n is convergent is an element on C sub 0 of R. Okay? Okay. From the step 2, we have proved that f sub n approaches to f as n approaches to infinity. Then, for every epsilon positive, there exists n in natural numbers such that for every n is greater than or equals to capital N, we have the absolute value of f sub n of x minus f of x is less than epsilon over 3 and less than epsilon for every x in R. Since the absolute value of f sub n of x minus f of x is less than epsilon over 3, then the absolute value of f sub n of x minus f of x is less than the norm of f sub n minus f is less than epsilon over 3. Next, we will show that f continues on C in R. Take any C in R. So for every x and C in R, we obtain the absolute value of f of x minus f of c is equals to the absolute value of f of x minus f sub capital N of x plus f sub capital N of x minus f sub capital N of c plus f sub capital N of c minus f of c. So this is equal to this because if we operate it, it will cost 0 and it will cost you this. Okay, this is from here to here is less than or equals to the absolute value of f of x minus f sub capital N of x plus the absolute value of f sub capital N of x minus f sub capital N of c plus the absolute value of f sub capital N of c minus f of c. And this all is less than epsilon over 3 plus the absolute value of f sub capital N of x minus f sub capital N of c plus epsilon over 3. Since f sub capital N is continuous, then there exists delta positive such that the absolute value of f sub capital N of x minus f sub capital N of c is less than epsilon over 3 for the absolute value of x minus c less than delta. Therefore, this is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3 is equals to delta. So the absolute value of f of x minus f of c is less than delta. So f is continuous on C, is an element of R. Next, we will show that limit of f of x as the absolute value of x approaches to infinity is 0. If the limit of f of x is 0, it means that for every epsilon positive, there exists capital M positive, say that for every x in R, we have the absolute value of f of x minus 0 is equals to the absolute value of f of x is less than epsilon from the definition, of course, from the definition of the limit. Now, we're going to take any epsilon positive. Since f sub n approaches to f as n approaches to infinity, then for every epsilon positive, there exists capital N in natural number, such that for every n is greater than or equals to capital N, we have the absolute value of f sub n of x minus f of x is less than epsilon over 2 and less than epsilon for every x in R. Since f sub n of x is in C sub 0 of R, then from the definition of f sub n of x approaches to 0 as the absolute value of x approaches to infinity, we have there for every epsilon greater than 0, there exists m is greater than 0, such that for every the absolute value of x is greater than or equals to capital M, we have the absolute value of f sub n of x is less than epsilon over 2 and less than epsilon for every x in R. Using the triangle inequality, for every n is greater than or equals to capital N, and the absolute value of x is greater than or equals to the capital M, we obtain for every epsilon positive, there exists m positive, capital M positive, such that for every x in R, we have this. The absolute value of f of x is equals to the absolute value of f of x minus f sub n of x plus f sub n of x. Okay? As you can see, this is equals to this, and this is less than the absolute value of f of x minus f sub n of x plus the absolute value of f sub n of x. So this is from the triangle inequality as I mentioned before. And this is, of course, less than epsilon over 2 per epsilon over 2, which is, this is equals to epsilon. So we have the absolute value of f of x is less than epsilon. So we already proved that the limit of f of x as the absolute value of x approaches to infinity is equals to 0, or f is an element of c sub 0 of r. Thus, f sub n converges to f in c sub 0 of r. And then we have, this is a complete space. We joined from the first information that we have proved. We have, this is a complete norm space. And then we have, this is a Banach space. So we have proved that X and the defined norm is a Banach space. I guess that's all the solution from right now. We already proved that a space is a Banach space. And I think this is the end of the video. Thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.